So with that, it is my pleasure to introduce our first keynote speaker for this morning. That's Robert Hodges, who is the CEO of Continuent. Robert has over 30 years of experience in database and application engineering. Prior to Continuent, he worked on object relational databases and transaction processing at Sybase. He also held senior engineering positions at Portera and Exogen Group, where he designed and operated software as a service applications. Robert is the original designer of Continuent's Tungsten solution. Welcome to the podium, Robert.
Thanks, Terry. Hi, everybody. So it's great to be here today. I would like to start, just so I don't forget it, by thanking Percona and the entire Percona team for setting up this conference. We are a Diamond sponsor, and one of the reasons we do it is these conferences are just great. It's a wonderful opportunity to get together, build the MySQL community, meet our customers. By the way, if you're here in the audience, welcome. Love to meet you afterwards. So we really appreciate the effort that Percona puts into this, particularly Courtney's team. There's a lot of thankless work that goes into getting everything ready so that I can just step up on stage and talk. So what am I going to talk about today? Well, my topic is how MySQL can thrive in the world of massive data hype. And what I'd like to do is, first of all, make my slides advance. There we go. Okay. So what I'm going to be talking about is 3 simple steps. It's a 3-step program to survive massive data hype and actually get some work done. And by getting work done, I mean build big systems that actually work. So everybody knows about big data, right? How many people have not heard about big data in this audience? Nobody. Oh, Peter hasn't heard about it. Well, Peter, we'll have to talk afterwards. So this is really big news, and it just has this really breathless quality. Here's just a typical thing from Wikibon, which is actually a wonderful open source website, a lot of information about analytics and big data. And there's just all these wonderful statistics, like Akamai analyzes 75 million events per day. The New York Times generates 11 million PDFs per day. It has this breathless quality about it that's very exciting. There's wonderful things happening. And it is true that even leaving aside some of the journalistic excess, we have our largest customer is very much involved in this. They process between 500 million and 1 billion transactions on MySQL per day. That's a lot of transactions. Everybody in this audience probably has a cell phone. Cell phones generate what are called data trails. It's kind of a beautiful but also kind of scary image of us going around and generating little blips of data every few seconds. So there's really something going on here. There's in fact a revolution in data management. It's not the first revolution that we've seen, and in fact, when these revolutions occur, as engineers, we need to respond to them. We don't want to be following the revolution. We want to be out in front of it. So here's a typical engineering response. New data management problems, it's time to rewrite everything. Anybody, who in the audience knows this guy? Professor Mike Stonebreaker? I know him. I haven't actually personally worked for him, but he has employed half the people in my hometown of Berkeley. So don't get me wrong, he's a great guy. But this is a very typical response to these new problems. And in fact, what we see is that when people see these problems, and particularly as engineers, we do think everything has to be rewritten, and then the question is what? And this kind of frenzy descends on us, and we are looking for things that we want to rewrite, and maybe not necessarily looking at the problems that we actually have to solve. I call this approach rounding up the usual suspects. And in MySQL, there are 3 particular suspects that seem to come up again and again. They just never die. The first one is transactions. Transactions obviously slow things down. We'll talk about speed in just a minute. But I was at a Cassandra conference, actually in this very building a few months ago, and I went to a talk where a guy from Instagram just went on this long rant about how ridiculous transactions were and how stupid we were to be using them. When I attend talks like that or hear anybody say that, my heart kind of sinks, because transactions are fundamental to software, and they're particularly fundamental to data management. And it's pretty easy to see this. If if you think about a piece of code that has a transaction, I'm not going to pick a bank. That's the usual sort of ridiculous toy example that people take. Let's just think about a social application, some sort of social network application that has followers. We'd like to insert a few followers for a particular person who's using this application. And you think about the code, there's a begin, if we're using transactions, there's a couple of inserts, and there's a commit. Transactions give us some important properties that we normally call ACID. So atomic, consistent, isolated, and durable. Let me just pick two of these and show how important these are. The first one is atomic. So this means that the application either succeeds completely or it fails. That's actually very valuable, because if you didn't have this, you would have to actually add extra code if you had an error to figure out how far you got through this list and restart at the correct point. As it is with transactions, if it succeeds, you're done and you don't need to worry about it. If it fails, just repeat the whole thing. This is very simple to understand, and practically anybody can do it. Another one is isolation. Isolation is incredibly important, and that's why I put 4 question marks beside it, because it's the one that's hardest to do without. It basically means we don't have to think about other things that other applications are doing at the same time. If you have to think about it, you're doing concurrent programming. It's incredibly difficult. And just to illustrate the difficulty, I do a lot of work on replication. We have one method in the Tungsten replicator that in the last month has supplied us with 3, not 1, not 2, but 3 concurrency bugs. This is a method with only about 4 or 5 lines of code. It started out with 3 lines. I've added about 2 more to correct the last bug. This is incredibly difficult to program. So if you don't have isolation, you then end up adding a lot of code, and in fact, you may never even be able to get it to work. And that's actually brings us to an important point about applications, or transactions, which is we don't have transactions to make banks work. That's an important misconception. We have transactions because they are necessary to make distributed applications work. And this is a quote from the beginning of a very famous book by Jim Gray and Andreas Reuter called Transaction Processing. It's one of the first things you read in the book. It's as true today as when they wrote it. So this is suspect number 2. It's a complete canard. Suspect number 1. Let's get on to number 2, SQL. I don't know what it is about SQL that inspires such hate, but there's entire websites that are devoted to ranting about SQL. Has anybody seen these? I found one where there were 1,800 rants. They even counted them about how bad SQL was. It's really pretty straightforward. So here's an example of, and granted, you have to learn it. It is different from procedural programming languages because it's dealing with data that's organized in sets. This is a little bit different from reading things out of a file or doing simple procedural logic. Here's an example of reading from the Sequila rental table. This is a demo database from MySQL. Some of you may have used it. And it's pretty simple to get a few items out of the table. Now, the question is, if this is really so bad, what do other database types use instead? So we can go check. And for example, we could actually go over to Cassandra. So this is an example, what you're seeing. I hope this code is large enough to read. This is an example of manipulating the Sequila table inside Cassandra. There's no new API. In fact, I entered the exact same queries as I did, or the exact same queries I did in the previous example, and I also got 5 rows back. They were 5 different rows because they cluster the data differently. But this is actually how Cassandra manipulates data. They use SQL. So it can't be that bad. In fact, it gets better. If you read the Cassandra, how many people here use Cassandra? So a few. It's an interesting database. I've actually learned a lot from it. If you go read the DataStax documentation, you find the following pronouncement. It is quite remarkable that you have CQL, which is the SQL-like language. It is the default and primary interface into the Cassandra DBMS. SQL is clearly not the problem. There are things that SQL doesn't handle, and we'll get to that in a minute, but SQL itself is not the issue. Suspect number 3, MySQL performance. So the following, I'm showing you 3 true statements. So very simple. MySQL is slower than Mongo, Vertica, and Cassandra. These are true statements. The problem is There's also other true statements which are just the opposite. MySQL is faster than Vertica and Cassandra. You can prove this yourself. I did a simple experiment using a couple of the computers in my closet at home. What I did was I just took that Sakila table, the rental table that we were just looking at a second ago, and I loaded it different ways into MySQL and Cassandra. So I started out with MySQL kind of lean and mean, no bin log, no fsync to disk on commit. This was 16,000 separate inserts, not using any cheaty techniques like block insert. Loads in about 2 seconds. Same thing on Cassandra. Depending on the number of nodes, you get something between 8 and 35 seconds to load. Clearly, MySQL is faster than Cassandra. But wait, we can actually tune up MySQL because maybe we'd actually like to make sure the data is totally durable. We have kind of a low-performance disk under there. We put the bin log on, we fsync everything, bang, all of a sudden MySQL takes 150 seconds. MySQL is therefore slower than Cassandra. You can pretty much prove anything with a performance test, but what it really comes down to is that when you're doing approximately the same thing, you want the same level of data durability, you're solving a problem that requires the data to be organized the same way. MySQL is very, very fast, and there's abundant proof of that. So we have here 3 pseudo problems, and these are not the problems that we need to solve. What we really need to do is the first step in this surviving massive data hype is to focus on real problems. I don't claim to know what all the problems are that MySQL needs to solve, but I'm going to give you 4 examples that come up in the systems that we work with and the customers who are using our software. Let me go ahead and start the first one. Highly available cloud operation. This is a really, really important problem. These are some sort of interesting numbers from Gartner. I'll say in advance, I don't know how much I believe them, but even if they're off by, say, 100%, they're still very thought-provoking. What this is showing, the lines on the graph, are the approximate or sort of estimated total installed instances. The red line is virtual operating system instances, that is to say running in a VM somewhere, and doing some sort of server activity, like running a web server, a database, or some other useful piece of software. The blue line, which is below it, is the actual number of operating systems installed on real hardware. So, and what's interesting is in this estimate, at least, the lines cross in 2013. That's the first thing. So the number of virtual instances, and in some ways this is a proxy for cloud operation, is now increasing rapidly where the number of installed operating systems on hardware is staying more or less at the same level. So this is, the virtual instances is increasing rapidly. Moreover, the numbers are huge. If you run this out to 2016, the estimates are that there'll be something like 70 million of these things worldwide. These are very, very big numbers. And in fact, in our own personal experience, 2 years ago, most people who came to us as Continuent customers were not using the cloud. Nowadays, at least 50% of them are, and just about everybody we talk to is interested in using it in some way. This is a problem we need to solve. Make MySQL operate in this environment and make it stay up. Next problem, large and variable data sets. So people talk about big data, but MySQL actually has a very particular problem to solve, at least in the applications that I see. This is an example of some data that was kindly provided by one of our customers. They have several thousand, there's a Saas operation, they have several thousand customers, and what we did was graphed the data distribution. Each customer gets their own schema in a MySQL database, and so we're graphing, thanks to, just by going out and doing df minus k, we can see how much space they're using. The biggest customer in this graph, this way out there, is using about 1.2 terabytes. The 99th percentile customer is using 290 terabytes. The median of these thousands of customers, that is the 50th percentile, uses 2.6. There's huge variation in these groups of data. Moreover, these are true shards. There's no connection between them, so you've got these clumps of data which vary from very small to very large that you need to manage efficiently. It gets better. If you go in and look at that big customer and ask yourself, where's the growth coming? There's an interesting pattern that I've seen in many SQL systems, and that is that when SQL systems grow big, they grow big because of a lot of processing on a single, sort of a lot of data added to a single table. And that's exactly true here. So the largest table in this system is 823 gigs. That's 2/3 of the data, the 1.2 terabytes that these guys are using. Moreover, if we take the top 3 tables only and pull them out, we're reduced to something like 200 gigs. And there's over 300 tables in this schema, so this is a very interesting, again, a very interesting example of where the growth in data tends to come in SQL systems. This is a problem that we need to solve to be able to manage this efficiently, especially in the cloud. Problem number 3, geographic distribution. How many people are running sites that have data in more than one location? Yeah, that's about right. So it looks like close to half of you. Continuent, we actually have our database for our website stored in 3 places. It's running in Amazon East, Amazon West, and we don't totally trust Amazon, so it's also in rack space. There's a lot of reasons why people need to distribute data. It may be availability. It may be the fact that you want to have data moving closer to customers so they get faster response. It may be things like regulatory requirements, like needing to have certain data processed in Canada because it's a Canadian business. Or you have tax reasons for wanting to process. We actually had a customer who had these tax reasons for wanting the transactions to be processed in a particular location. This is problem number 3. And problem number 4 is what is commonly called polyglot persistence. This is a great term. I think it may have been coined by Martin Fowler. And what it means is there are many types of databases. SQL is not the enemy, but SQL cannot solve every problem. There are some things that are just not modeled well by sets, graph problems, for example. There are different ways of storing data. MySQL is a row store. There are certain problems that require data to be in columns. There are certain problems where it's very useful to have the data stored as aggregates, as we do in MongoDB. Because of these problems, we now are in a world where people are going to have multiple databases. So for those of you that run MySQL, how many of you have another database besides MySQL in your data center? Okay, it's a good number. It looks like about 1/3. It is increasing. Every large customer that we work with has a database other than MySQL. So we need the ability to kind of get along with the neighbors and work in this environment. So that brings us to step 2 in the program for surviving massive data hype. And we need technology improvements, and the one that we're particularly focused on at Continuent is something that we call database as a service, and I want to add an adjective. I want to call it cloud scale database as a service. In other words, turning a database into a push-button store that can be brought up easily, managed easily with a few clicks. This is very much the Amazon model, where you build systems sort of on the fly. You can just punch a button and things come up and run. We need to be able to do this with MySQL. And rather than explain more about it, I think what I'm going to do is give you a demo. So let's see if we can switch over here. There we go. I have to put my glasses on for this. Okay, so what we have right here is a user interface that we're currently working on at Continuent. It is based on our clustering software, the stuff I mentioned that we have a customer doing 500 million to 1 billion transactions. It is that same software underneath. We're now working on a UI to make it easier to manage and to implement database as a service. I want to say this UI is not ready yet, but we're giving you a preview to show you what can be done and also to show the vision of how great database as a service can actually be when it works. So what we have right here in the screen on the left side is I've set up a cluster, and unfortunately it's a bit small, but bear with me. It's a USA cluster, so it actually consists of a couple of sites, and I'm going to go ahead and open them up. So I'll just click on it. I get a west and an east site. So one on the east coast, one on the west coast. These sites actually have a master-slave relationship with each other. So this is a multi-site data service, as you'll see in a moment, or you'll see shortly. And if I click on the west data site, which is the primary, where the master lives, I see that I have a master here, and I also have a couple of slaves. Now, if your eyes are good, you'll notice that 2 of these slaves are offline. What I'd like to do is, I've got a load running on this right now. It's putting in about 500 writes per second, and it's getting about 1,500 reads per second on this system. What I'd now like to do is begin activating these slaves to add capacity to this system. Let me go ahead and do that, and watch what happens over on the right when we turn the first slave on. So up it goes, it's now online, and what we're going to see in any moment now is we're going to see our graph. There it goes. It's got a little bit of hysteresis as it collects data. It's now going to jump up and begin processing more reads. What's happening here is that the clustering software underneath, as you'll see, as I'll describe shortly, has very flexible connectivity that knows how to do read-write splitting automatically. As soon as it detects that the new node is online, it begins shifting reads where it's safe to do so onto the slave. And a couple of things happen. Obviously, we get a bounce in the read performance because it's moved off to the slave. The other thing is it's good for masters. The master, we see the master capability bounce up a little bit. It's also stabilizing because it's not contending with the I/O for reads. We can bring another of these guys on. There we go. So we'll add the slave, the last slave, and we're up and running. You can see the master performance is kind of stabilized. Oops, there it goes down a little bit. So anyway, we now have the system operating at full capacity. So we're beginning to see the jump from reads from the second slave. And actually, if you can see this, if you're sitting close enough, you'll notice we have some little numbers that show the numbers of connections. They're beginning to balance between the two slaves. And based on the load on the slaves, we switch them back and forth to make the capacity, to balance the capacity nicely. Let's say we need to do some maintenance. It's a very important problem because there's a lot of things that you have to do that require you to take a database offline. Perhaps you're going to do a software upgrade. What I'd like to do is I'd actually like to go work on my master. Maybe I'd like to increase it to a larger instance size in Amazon. What I'm going to do is take one of my slaves, just punch the button, and promote it. So this is an operation internally. If you're a Continuent customer, you know of it. It's a switch. What we are doing is in the background, we are halting the transactions coming into the master. We are basically, and then we're taking some special steps to make sure that the slave we're promoting is fully caught up, and then we're going to reconfigure the systems and open everything back up for business again. So you see a dip in capacity on the graph while this is happening, but then within a few seconds, the switch completes and we're back in operation again. The interesting thing about this operation, and it looks like we're getting a little bit of, the switch has finished, but it looks like we're getting a delay in the UI updating. The switch is actually finished and the application is continuing to run. So, and here we go. The UI is updated and now DB2 is the master. So basically this enables us to do transparent maintenance. And as you look at this, we're already solving a lot of the problems that we see in the cloud. These are to have an availability model that allows us to spread things over multiple regions. That's what's being solved here. We're also able to take things offline without the applications noticing so that we can do maintenance, make changes, but continue to offer complete service to our users. These are very, very important in cloud operations and 24/7 systems. The other thing that can happen is the world is an uncertain place, and every now and then things get killed. So let's go ahead and just kill that master. And just so that I get my kill all command, I'm just going to do a kill command, kill -9 on the master, and this is going to zap it. So let's just go ahead and run that command. So nothing up my sleeve. Oops. We need to sudo that. Sorry about that. All right. That should be a little bit better. So we've just killed the master. If we come back and look at our graph, what we're going to see is actually, if you have good eyes, you can already see that we marked DB2 as failed, and we've moved it down in the list. It's now shunned. This is automatic failover. A lot of people think it doesn't work. We beg to differ. So this is shunned. It's now waiting for somebody to come look at it, see what happened. We don't want to bring it back because that can cause further failures. But meanwhile, the cluster is back in operation. Everything is proceeding as before. So what we can then do is we've got this guy that's broken. Let's go ahead and fix him. So we're going to do a recovery. And what this is doing is it's going to go grab our latest backup and we'll actually start the server if necessary. It's going to grab our latest backup, restore it, and then bring this guy back as a slave. So this is repairing the instance, and in fact, that was pretty good, pretty quick. This is not a big data set. We're basically up and running again. So basically what we have is you see database as a service in action through this very simple UI, push-button operations. We can go further because we've just been working on a local data service. Let's see what happens when we want to make a switch and actually move the primary to our East Coast setting, or to our East Coast site. It's very simple. We just go back up a level in the hierarchy, and we're going to just run a promote on the East Coast cluster. This is now promoting an entire cluster. So if you watch the, again, watch the graph, we will see that this will eventually switch. There you see it happen. So it's kind of a nice effect. It flips in the UI, and now the East Coast is our master. And then there's one final thing I'd like to show you about this cluster before we stop managing it. If we go into the East Coast, we've now got a master. Everything's online. If you can read the connections, we've actually got 141 connections right now, or 125, over 100 connections going to our master. But interestingly enough, we have no traffic going on the slaves. Yet we still see reads continuing. What's happening here is that the connectivity underneath is very smart, and it has something called site affinity. It knows that if we're doing a read, we can afford to go on a replica, first of all. Second, we're going to look for a replica that's nearby. So in fact, the reads have not actually moved off the West Coast site. They're still going against the West Coast. So this again illustrates some of the powerful capabilities in database as a service that turn this off-the-shelf MySQL, this building block, into a very powerful into a very powerful system for managing data. So finally, if we want to make more of these, we can just go ahead and hit the bottom of the screen. There's a palette here. We have various patterns for clustering. For example, if we want to make a new multi-site data service, we go ahead and fill in a new name. I could, for example, call it Atlantic. And this font is way too small. I apologize for that. It's not good for demoing in a big hall like this. But basically, if you'll take my word for it, I can go ahead and fill out 3 or 4 screens, click Launch, and I'll now have a new cluster that looks just like this one. It won't have the same data, but I've now got another one which is up and ready for use. So with that, I'm going to drop off the demo, but I think this gives you a sense of what it is that a database as a service really looks like when it's fully implemented and where we need to go. What I'd now like to do is tell you a story about what we have done underneath to make this work, because this is something that we have been working on for quite some time. So we'll flip back over to our talk. All right. So the starting point for this, and this is where we at Continuent started many years ago, was to take MySQL as a building block. MySQL is a great database. I've now been using it for over 7 years. Particularly with the last few releases, it is a very, very good store of data. It is transactional. It is very rare. How many people have lost data recently in NoDB? Let me just put it that way. One person. You, sir, have been very unlucky, or ma'am, as the case may be. So, but it really, you have to work to lose data in NoDB. It's a very powerful database, and it's a great building block for building this database as a service. The next thing we do is we add replication. This is one of the things that MySQL has really pioneered, is master-slave replication and building redundant systems using replicas. What we do inside Tungsten is we go one better. We like master-slave replication, but we have our own replication which basically replaces it and adds a bunch of interesting capabilities. So the replicator reads from the master. Of course, we parse the bin logs. We then pull it over to the slaves, and we can apply in parallel. This is actually something that that's now operating in production with some of our largest customers. In one case, it reduced slave flag by a factor of over 100. So this logical replication is the first step to building a redundant service. The next thing we want is resiliency. So what we're going to do is we're going to add cluster management. And so in the Tungsten architecture, we have little manager processes, Java processes. They run on each of your database nodes. And they are basically responsible for watching what the databases are doing, watching what the replicators are doing, communicating that to the other members of the cluster, and then allowing you to log into any manager, see the state of the cluster, and perform operations. So that's how we did the management operations, like being able to do a promote, was we called up one of these managers and said, hey, go ahead and switch to whatever server I'm pointing at right now. The other thing that the managers do to get full resiliency is they include the automated failover. And this is a clustered system. It uses group communications. If something fails, one and only one manager pops up and takes control and does its best to fix the cluster. Next, we add the routing. This, in some ways, is the secret sauce. You saw it in the graphs that we were just showing a few minutes ago, that where the routing is coming through, we're transparently finding the master. This is pure software. What we do is we add this connectivity layer. We call them connectors. They look just like MySQL servers to your applications. They fully implement the MySQL network protocol, and they create this very powerful illusion to your applications that there is one database out there, whereas, in fact, there are multiple replicas that may be in different states at different times. A master, a slave, online, offline, lagging, not logging, lagging, so on and so forth. The connectivity allows us to do this, and this is the capability that then allows us to do transparent maintenance, for example, or be able to reconfigure the system without stopping applications. Finally, backup and restore. I'm going to come back to backup and restore, but I can't tell you how important this is in these redundant systems. You need the ability, you need to be able to provision new copies of data. You need to be able to fix things that are broken by reloading a copy, setting it back to an earlier state, and then having it catch up to where it was before. So we have backup and restore. We use, for example, for medium-sized data sets, or small ones like this, we use the Percona Extra Backup. It's an excellent piece of software, and that we depend on every day. So basically, you've got a database as a service. You can think of boxing this up and adding a management API and GUI administration like what I just showed you in this preview, and you've basically got a service which can now run in a cloud environment. Moreover, it can run in multiple regions, so on and so forth. So this is your database as a service. So your applications connect to it, the database is always on, and you can manage very large quantities of data. We can take this further because this is a pattern, it's a building block. Of course, it allows us to build the primary and DR patterns that I just showed you in the GUI demo. We can also do multi-masters. So in those cases where you're geographically distributed, everything needs to be fully active so that you can have writes on any of the masters. That's another pattern that you can implement with this database as a service. And finally, we also have the ability to do real-time integration with other data sources. So I mentioned this polyglot persistence, which is this very important problem. Now, most people, particularly Martin Fowler, when he's talking about it, he's thinking about NoSQL. Actually, the real polyglot persistence comes up with legacy databases like Oracle. So we can replicate data bidirectionally from Oracle. We're doing that for a number of customers now. And actually, just this week, we announced that extraction of data out of Oracle is also in open source. So our replication capabilities are fully open source. Moreover, we can replicate out, again, in fully open source, to all kinds of other data sources. So MongoDB, Vertica, and Calpont are just three that we can support. We're always looking for other, we're sort of slowly adding others as they come up. But the point is here that this is again a pattern to move data in real time using the replication and be able to knit data from different stores together. And in fact, what this really leads to is, so far we've been talking purely about implementation, but as you can see, we're building it up in a kind of systematic way that actually follows from a set of design patterns. And what this really led us to over the course of the last year was to realize this is not just an implementation for data management. This is an architecture for large-scale systems that manage data. We call this architecture data fabrics, or data fabric architecture. And so what you can do is you can take these patterns that I've been describing and you can reduce them to design patterns which are relatively easy to understand, and then form composable building blocks that you can use to build large systems. So for example, the MySQL database within ODB is a design pattern that we call a transactional data service. It's a standalone database that processes transactions and has recovery. Fabric connectors. This is something that finds your data without your application having to know where the data are located. Fault-tolerant data service. That's the basic single-site data service with redundancy and failover and automated connectivity to make it look like one database, so on and so forth. So what we have is not just an implementation, but also a way of building systems that even if you don't use our software, of course we're building to this pattern, but it's a way to think about building these systems and having them work in the cloud as well as on-premise. And in fact, if you look at thinking about any system that you have right now, you can take these design patterns and think about how you take your current system and reorganize it along these lines. And our goal here is to go from, everybody here has worked on systems that look like spaghetti, right? I've created those systems. You're in a hurry. You often don't fully understand the technology, but with the design patterns, you can now begin to refactor the systems in a way that they're maintainable, they're extensible, they're not too expensive to operate, and that you can continue to run them for decades. And that's, if you think about what we're doing right now, the systems we are building today, if we're successful and the businesses are successful, they will be running 20 years from now or longer. So this is the second step in the surviving massive data hype, and that was to build the cloud-scale database as a service. I'd like to get on to the third step. So far, we have been talking about using MySQL as is. It's a black box. We take it as a building block, and we build big systems around it. It's great for that. But at some point, you have to look inside MySQL and say, what can we do in MySQL to make it better? And I don't have a full view of every problem that needs to be solved in MySQL. There's just such a variety of applications. But I will tell you that there are some improvements that we can see from the systems that we're building based on this data fabric model. Let me go through them. So the first one, before I explain what it is we'd like to see, I have to explain what the problem is. So how many people here do multi-master replication? Okay, about 10%. Yeah, it's kind of scary, isn't it? But perhaps this problem is obvious to you. But in multi-master systems, you have multiple servers. They may, for example, be running on different sites. Each site is open for writes. And we can imagine that updates on the same tables and even the same rows in the tables are occurring in different locations. So in this example, we have a couple of updates on the right where one application on one site is updating a value with the same key as on another site. This is a possible conflict. And the question is, when did it occur? When did these updates occur and in what order? Because if one update occurred Monday and the next one occurred today on Wednesday, we don't have a problem. And in fact, in distributed systems, time is fundamental. This is one of the things that you have to grapple with because time implies causality and the ordering of transactions. So, one of the things that would be really nice to see in MySQL going forward is to give MySQL a sense of time. And I'll just give you some examples going from relatively simple to quite complex. The first is just to put automatic timestamps on rows. So a lot of us do this already. You put an updated column out there and you update it. MySQL does this. Let's just make this something that's automatically there that you can turn on just like an auto increment key. Make it a UDT. It turns out that there's different schemes of time. We normally think in terms of things like seconds or microseconds, but there's also logical clocks, which is another form of time that distributed systems use. Make it a UDT, we get to pick, and then we can assign the values correctly. Then it gets harder. If you're doing conflict resolution, it would be wonderful to be able to see the old rows. Like, don't throw rows away, but keep the old ones around for a while just in case we need to roll something back. Cluster them on the primary key, and at that point, you can begin to implement something like Cassandra's automatic conflict resolution. This is a very powerful feature, and I think one that is, given the innovation that goes on in replication in MySQL, is one that we should consider. And then finally, enable what are called globally consistent reads. And this is like an Oracle flashback query. Give me the state of this table as of this time. This is useful for a number of things, but particularly to be able to make sure that the tables are consistent as of a particular time. This is important to understanding whether your system is working right or not. So that's suggestion number one. Suggestion number two is to embrace sharding. I think one of the things in MySQL is I think we're all secretly ashamed of sharding. We should really have an infinitely scalable store, horizontally distributed, and we wouldn't need these stupid shards. But the fact is that just about everybody that builds systems uses shards. Let's actually put some stuff into the database to make that easier to do. Just make them first-class objects. Maybe they're schemas. That's what a lot of people, in effect, use. But let's actually add some support to make them work right. So, for example, if you have a shard, if you're using schemas as your shards, put in a feature so you can't have a transaction that crosses shard boundaries. It makes it very difficult to do things like parallel replication if people are doing that kind of stuff. Handle a mix of shard sizes. So we saw this enormous variation in the data size. You must be able to handle a tiny shard and a very large shard. We deal with data that's often very, very lumpy. Move shards at the storage level between servers. There's actually some very cool features in 5.6, I believe put into for SSD performance, but the ability to move the .ibd files around. This is exactly what we want. Let's move it up a level and actually make it work for an entire shard. So if we do this, we're going to go a long way to making MySQL the database of choice for both Saas as well as any other application that uses shards. These are explicit shards where the application knows about them. Suggestion number 3, backup. So one of the big problems with MySQL is that as soon as you get over 1 terabyte of data, it's very difficult to do a backup. In fact, in most of the systems we deal with, if you don't have a SAN, it gets very tricky because you need something that can take a snapshot of the data. Extra backup, we love it, but at that level, to dump and reload data is about a 24-hour operation. This is not really suitable, and it obviously doesn't scale. So being able to have solutions that allow us to back up very large data sets, and when I say large, we have people who are running 7 terabytes per server, being able to back up that level. Parallel dump and restore, do fast shard restore, integration into cloud storage. And it would be great to eliminate SANs. But the interesting thing is you do have them in the cloud, for example, through things like Elastic Block Store. If we can't get rid of them, maybe we should just embrace them and do everything we can to have MySQL have modes of operation that are tuned to SAN so that these backups will work. The benefit is that we have the ability to create the replicas that are necessary for HA and scaling. And there's a final thing, which just has to be done in the database, and this is large table support. So there's 5.6, as we're going to be talking about in a few minutes, has some wonderful improvements on performance. But I think that this is something where there's still a long way to go. The cloud is kind of a step backwards in some respects because we can't have these huge vertically scaled sort of systems with 256 gigs of memory. You just don't get that in the cloud. They're cost prohibitive. People want to be using smaller instances that they can kind of dial up and dial down. Enabling fast queries, so whatever is necessary, everything from parallelization to better partitioning, you name it, sort of straight query performance is important. Being able to do online maintenance, 5.6 is making a great step forward. Let's really make this work on very large tables. All of these operations tend to kind of screw up as soon as, as you go to 100, 200, 300 million lines of data, that's when you start to see some ugly problems. Fast checksum, so you can check the consistency of these tables. If you've got replicas, being able to identify that pieces of the table are in a certain state, that's very useful for ensuring that systems work. And compression, the list is kind of obvious, and I think there's kind of an open question, which I don't know what the answer is, but a lot of the NoSQL databases do auto-sharding, where they explicitly break the databases or tables into invisible shards, which are then distributed across multiple machines. Maybe MySQL needs to do that. It is a way of handling these very large tables. It's definitely something that we should consider. This is going to keep us in the game for dealing with large data sets. One thing that MySQL does not need is a rewrite. We have something that already works. And so to go back to Professor Stonebreaker's point, we do not need to rewrite MySQL. It already works. The other thing is rewrites often don't work. These are a couple rules from Kurt Monash. It costs a bundle to do a rewrite, and it takes a really long time. We don't lose data in NoDB anymore, at least not much. I don't know if there's anybody in this audience who wants to go back to losing it again. We don't need that. The other thing is nobody is an exception to this. Every database takes a long time to, new databases, new stores take a tremendously long time to mature and become reliable. So the final thing inside MySQL and overall is to learn from the NoSQL and the analytic databases. There is a revolution going on. Some of the ideas that I've proposed here for adding time to MySQL are based on looking at Cassandra and also reading some of the academic work that's going on. There's just a bunch of new ideas. There's some bad ones out there, like getting rid of transactions. We can just pass over that in silence. But we can learn from the good ones. Great example, dynamic columns in MariaDB. This is a really cool feature. I haven't tried it out yet, but this is exactly the kind of idea that we should be trying out to give MySQL the capabilities of a column family store like Cassandra or HBase. That's a really cool idea. So I think we want to take some chances and see if we can build a better MySQL. And at that point, we've created MySQL that actually thrives in the world of big data. So we don't just survive this hype, but we actually feed on it, and we build MySQL. We enhance MySQL, we enhance the infrastructure around MySQL, and we allow people to build big systems that will last for decades. So, in conclusion, with this brief recipe, the data hype problem is solved, and there's just 3 steps. Once again, focus on the real problems. They're not the usual suspects. Actually look at the data, figure out what people are doing, solve those problems, and make their life easier. Put database as a service on top of this, and we've shown you an example of what this can look like, and for Continuent customers, what it will look like a little later this year, and then build a better MySQL underneath. It's a very simple recipe. Okay, and with that, I think I'm done. Thank you very much for your attention. See you at the conference.